My dear students of Rajakuttara Model College English Medium section, I hope you are well at your residence. Today I shall discuss some periodic properties. It is chapter 4 for 9-10 students and chapter 3 for 11-12 students. The class is equally important for the students from class 9 to 12. Today we shall discuss the following points. Number 1, atomic size. Then number 2, ionic radius of cations and anions. And finally we shall discuss ionization energy or ionization potential. At first, the atomic size or atomic radius. What is the change of atomic size in a period from left to right? As we move from left to right in a period, number of protons in the nucleus and the number of electrons in the outermost energy level increases, but number of energy levels remain same. As a result, attraction between nucleus and the outermost energy level increases, and so atomic radius decreases gradually. Let us try to understand with the example of the element of second period. Lithium is the first element. Lithium is the first element of the second period. It has two energy levels. It has 3 protons in the nucleus and 1 electron in the outermost energy level. For the next element, the number of energy level is again 2, but the number of proton is increased by 1. Now the number of proton is 4 and the number of electron in the valence shell is 2. Since the number of energy level is not increasing at all, but the number of proton in the nucleus and the number of electron in the valence shell is increased by 1, the attraction between the nucleus and the outermost energy level increases in case of beryllium than lithium. So the size of atom of beryllium becomes smaller than that of lithium. Similarly, for the next element, boron, 1 extra proton will be added in the nucleus and 1 extra electron will be added in the outermost energy level, but the number of energy levels will remain unchanged. For this reason, the atomic size will further decrease. So in this way, the atomic size of the elements of the same period from left to right decreases gradually. I have given the values of atomic radius in nanometer. You have to memorize these values for answering the MCQ questions. Let us see the change in a group. In a group, you all know the electronic configuration is same in the valence shell, that is in the outermost energy level, but in a group, as we move from top to bottom in a group, an extra energy level is added in each period. As a result, atomic radius of the elements increases gradually from top to bottom in a group. Let us start with lithium. I have taken group 1 as the example. Lithium has 2 energy levels. The atomic radius is 0.123 nanometer, and sodium has 3 energy levels, 1 energy level more, and so the atomic radius has been increased from 0.123 to 0.157. Potassium has 4 energy levels, so the atomic size is bigger than sodium, and so on. I have given the values. You have to memorize the values. Since in every case 1 energy level is added, so the atomic radius will increase, that is the atomic size of the element increases from top to bottom in a group. So what is the summary about the atomic size? The atomic size decreases from left to right in a period, but increases from top to bottom in a group. Now let us proceed to the radius of cations and anions. The radius of cation is of course less than that of the respective element, because when an element forms cation, it loses the electron from the outermost energy level. As a result, the outermost energy level is vanished. So the number of energy level in case of the cation is less than that of the respective element. For this reason, the size of the cation is smaller than the respective element. Let us think about one example at least. Sodium, it has 3 energy levels, but when it loses one electron, it forms sodium ion, which has 2 energy levels. Sodium atom has 3 energy levels, but sodium ion has 3 energy levels. Sorry, sodium atom has 3 energy levels, but sodium ion has 2 energy levels, that is one energy level less. For this reason, the atomic radius of sodium ion is less than that of the sodium atom. So the summary is the size of the cation is smaller than the respective element. Now, if same element forms different ion with different charge number, then what will be the difference between the ionic radius? The ion with higher ionic charge, the ion with higher oxidation number will be smaller in size. For example, between ferrous ion and ferric ion is smaller in size, because in case of ferric ion there is one electron less in the outermost energy level than the ferrous ion. As a result, nuclear charge per electron increases and so ionic size decreases. In case of ferrous ion, 24 electrons are attracted by 26 electrons, but in case of ferric ion, 23 electrons are attracted by 26 protons. So the nuclear charge per electron increases in case of ferric ion than ferrous ion. For this reason, ferric ion is smaller in size than ferrous ion. What about the radius of anion? When an element becomes anion, it receives electron. By receiving electron, it gets the electronic configuration of the nearest inert gas. For an example, oxygen. Oxygen contains 6 electrons in the valence shell. For fulfilling the octet, it accepts 2 electrons and it becomes oxide ion. That is, the anion contains more number of electrons in the valence shell than the respective element. For this reason, nuclear charge per electron decreases when an element is converted into anion by receiving electron. Since the charge per electron decreases in case of anion formation, the size of anion becomes bigger than the respective element. The atomic size of oxygen is 0.73 angstrom atomic radius, but the ionic radius of oxide ion is 1.401 angstrom. That is, oxide ion is bigger than oxygen atom. Similarly, chloride ion is bigger than chlorine atom. So the summary is the size of the anion is bigger than the respective element, which is just opposite in case of cations. Now our very important point, ionization potential. What is ionization potential? You all know, when an element loses electron, it becomes an ion and it becomes a cation. And for removing this electron, some energy is required. In gaseous state, of course, you have to mention that in gaseous state, the amount of energy required to remove one mole electron from the outermost energy level of 1 mole isolated atom and to produce 1 mole unipositive ion is called ionization potential. What is unipositive ion? The cation or positive ion whose charge is +1. That ion is called unipositive ion. When an element will lose one electron, it will get one charge. This charged particle is called unipositive ion. For removing this electron, some amount of energy will be needed. That energy for 1 mole atom is called ionization potential. And the energy needed to remove one electron from the outermost energy level is called the first ionization potential. Normally, the term ionization potential is used for the first ionization potential. Let us have an example. When sodium loses one electron, it produces Na plus, that is unipositive sodium ion. 496 kilojoule energy is needed to produce 1 mole sodium ion from 1 mole sodium atom in gaseous state. So the ionization potential, that is the first ionization potential of sodium, is 496 kilojoule per mole. Now, what is second ionization potential? When an atom has already lost one electron, it has become an unipositive ion. If we like to remove another electron from an unipositive ion, we need to supply some more energy. In gaseous state, the amount of energy required to remove 1 mole electrons from the outermost energy level of 1 mole unipositive ions and to produce 1 mole dipositive ions is called second ionization potential. Let us think about the equation. M plus means an unipositive ion. You have to apply some energy for removing another electron, that will give you dipositive ion. For this purpose, the energy needed is called second ionization potential. For example, if we like to remove one electron from one sodium ion, that will form one dipositive sodium ion, and that will require a huge amount of energy, that is 6,912 kilojoule energy will needed for per mole of sodium ion. So the second ionization potential of sodium is 6,912 kilojoule per mole. Now an important point, that the value of second ionization potential is always higher than the first ionization potential, because in case of first ionization potential, electron is removed from a neutral atom. As a result, less energy is required. In case of second ionization potential, electron is removed from an unipositive charged particle. As a result, more energy is required. Let us elaborate this point with an example. When we remove one electron from neutral potassium atom, it requires 418 kilojoule per mole energy. But if we remove one electron from one potassium ion to produce one dipositive ion, then 3070 kilojoule per mole energy is required. That is, the second ionization potential of potassium is much more higher than that of the first ionization potential. What is the cause? I would like to remind you that when we remove one electron from a neutral atom, less energy will be required. So the first ionization potential will be less, but for removing the second electron from a charged particle, more energy will be needed. For this reason, the second ionization potential is always higher than that of the first ionization potential. And now we shall discuss the periodic change of ionization potential. In a period from left to right, the ionization potential increases gradually. Why ionization potential increases? Because the number of proton in the nucleus increases gradually from left to right. As a result, the attraction over the electron of the outermost energy level increases gradually. For this reason, the ionization potential increases from left to right in a period, though there are some deviations or exceptions. I have shown those exceptions with red color. That is, from lithium to beryllium, ionization potential is increasing as the normal rule, but in case of boron, it is decreasing, that is the ionization potential of boron should be more than beryllium, but practically it is less than beryllium. In the next slide we shall discuss these deviations. Another deviation is present also in case of oxygen and nitrogen. The ionization potential of oxygen should be more than that of nitrogen, but in fact it is less. We shall discuss this point in the next slide. Okay, let us proceed. What is the change in group? Ionization potential decreases from top to bottom in a group. It is very natural, since in a group from top to bottom, in every case one extra energy level is added. The attraction between the valence shell electron and the nucleus decreases gradually. For this reason, less energy is required to remove one electron from the outermost energy level. So ionization potential will decrease gradually from top to bottom in a group. I have given the example of group 1. The ionization potential of lithium is 525 kilojoule per mole, whereas sodium it is somewhat less, it is 500. For potassium it is 424, and it is decreasing gradually from top to bottom in a group. Let us discuss the exceptions. Let us discuss the exceptions. Ionization potential of boron is less than beryllium. The ionization potential of boron should be more than that of beryllium, since boron is placed after beryllium in the same period, but it is just opposite. What is the explanation? The electronic configuration of beryllium is 1s2 2s2. It has a full field electronic configuration. When it loses one electron, it gets the electronic configuration 1s2 2s1. Half field electronic configuration is less stable than full field electronic configuration. In case of boron, when one electron is lost from the outermost energy level, it gets the electronic configuration 1s2 It is a full field electronic configuration. Since after removing electron from boron, full field electronic configuration is attained, it is more stable than beryllium plus. So the ionization potential of ionization potential of boron is less than that of beryllium. Another exceptional case, the ionization potential of oxygen should be more than that of nitrogen, but in fact it is less. What is the explanation? The explanation is almost similar. The electronic configuration of nitrogen is very much stable. It has half field electronic configuration, that is p orbital can accommodate a maximum of 6 electrons. It is containing 3 electrons, that is it is half field electronic configuration, and the electrons are homogeneously distributed. Every p orbital, px, py and pz getting 1 electron each. When one electron is removed from nitrogen, the stable configuration is broken. But in case of oxygen, when one electron is removed from p orbital, that is from px orbital, it gets half field electronic configuration, which is very much stable. So by removing one electron, half field electronic configuration is destroyed in case of nitrogen, but in case of oxygen, half field electronic configuration is established when one electron is removed from 2px orbital. For this reason, less energy is required to remove electron from oxygen than in case of nitrogen. So the ionization potential of oxygen is less than that of nitrogen. This is the last discussion of today's class. I have given you some homework. You have to do this homework within 2 or 3 days. I have also given you some MCQ question. Please solve these questions and study this part of this chapter sincerely. This is very important part. Stay home, stay well, and study chemistry seriously. Okay, thank you very much for being with me. Thank you.